Hey everybody, Dr. Retzik here. This is our third video in 7a, where we're going to start specifying even further. We have been studying adjoints of linear mappings between inner product spaces. Starting now, we're going to require that the mappings be operators, so they map V to V, rather than the more general V to W. Let's get started. So, suppose T is a linear operator on V. V is some sort of inner product space. And so visually, we have this picture. Got a big box called V. T acts on V, takes inputs from V, and spits out outputs in V as well. The first thing that we want to do is kind of a funny little technical statement that seems totally out of nowhere and will only be useful to us moving forward Friday and perhaps again early next week. But for the moment, it seems apropos of nothing, but it's worth knowing. So here's this funny little result. Say you got U in V. You can do T to it, and that will land you over here at TU. And maybe you got something else in V, like W. And you might be interested in doing the inner product of TU with W. Observe, a four-letter word in math class. Observe, well, if you wanted to do TU with W, well, you could write it this way if you felt like it. Not saying you would, but you could if you felt like it. TU inner product W is the same as T acting on U plus W, inner product U plus W, minus T acting on U minus W, inner product U minus W, all over 4, plus inner product T acting on U plus IW with U plus IW. Take away inner product of T acting on U minus IW with U minus IW, all over 4, all times I. Obviously, right? Totally not obvious. And you would only convince yourself of the truth of this statement by actually working out the right-hand side. Like a bunch of stuff cancels, and you just get twice inner product TU with W over 4 plus twice inner product TU with W over 4. So you just get inner product TU with W. When the dust settles on the right-hand side, that's all that's left. You can just believe in this for now. It doesn't matter that we wouldn't necessarily think to write that out. It kind of reminds me of problem 20 in 6a, which you guys did on homework. But apart from that, it just kind of seems out of nowhere. Now, if we believe in this funny little fact, then check this out. This first chunk here is T of something, inner product, that same thing. The second chunk is T of something, inner product, that same thing. Third chunk, T of something, inner product, that same thing. Fourth chunk, T of something, inner product, that same thing. So one thing that this accomplishes is it allows us to see an inner product of something in the range, Tu, with some random other vector, W, as some kind of combination of inner products of the form T thing, comma thing. And in particular, if you were in a complex inner product space where you could do this, and note, this is important. If this is a real inner product space, then none of this blue underline stuff makes any sense. And in point of fact, this is not possible to write out Tu inner product W in terms of T thing, comma thing, if we're in a real inner product space. So it was critical here that we had a scalar whose square came out to -1. That was important for the dust to settle in the right way. If you believe in the fact, then you get a little theorem. And the theorem says, if V is an inner product space over C, and T, an operator on V, satisfies inner product TV with V equals 0. For all V in the space, then in fact, the operator is the 0 operator. It's the only one that can possibly have this property. Okay, so let's think about why that is true. The reason is in our funny little arithmetic fact. Looking back at that equation, if your operator T satisfies inner product TV with V is 0 for every vector, well, then this would be 0. Because that's T thing, comma thing. And this would be 0. Because it's T thing, comma thing. And this would be 0. T thing, comma thing. And even this would be 0. Because it's T thing, comma thing. Well, the whole right-hand side would be 0 for any operator satisfying this. So if TV inner product V equals 0 for every V in your inner product space, then Tu inner product W equals 0 for all U and W in the inner product space, because that's the left-hand side of the expression above. And the right-hand side is 0. So the left-hand side is 0. In particular, since Tu inner product W is 0 for all vectors U and W, then in particular, TU inner product TU is 0 for all U, i.e. T sends everything to 0. And that's the end of the proof. So if you're in a situation where you know TV is always orthogonal to V, and you're in a complex inner product space, well, then your operator is the 0 operator. That's the only operator that can do that over complex space. Now again, let's stress this. This is not true over the reals. Just think about the operator on R2 that rotates vectors by 90. That operator, surely, outputs are always orthogonal to inputs. TV inner product V is 0 for every vector. But that rotation by 90 degrees, that's not the 0 operator. So this theorem is totally false if you're talking about an inner product space over the reals. But at least if it's over C and you have access to this number called I, whose square happens to be -1, that means you can do that arithmetic trick. And in any setting where you can do that arithmetic trick, the only operator that satisfies outputs orthogonal to inputs is the 0 operator. Okay, this theorem will be important to us tomorrow. For now, it's just this interesting little fact about linear operators on complex inner product spaces. Now, the only other thing we want to do today is get even more specific. Remember, this is our picture right now. You got a box called V. You got an operator called T. It takes inputs from V and returns outputs in V. Okay, well, this operator has an adjoint. T star, where, remember, T star works like this. This is its connection to the original T. The inner product TV with W comes out the same as the inner product V with T star W. That's the defining feature of the adjoint. That's how the adjoint is defined. Okay. Now, Hayden was asking in class, was there a connection between, say, T star and T inverse? Because in the pictures, it really kind of does look like, T runs left to right and T star runs right to left. And so it sort of reminds us of that symbiotic relationship between T and T inverse. And my answer at the time was no. I mean, it's possible T star could be T inverse, but there's no expectation. Okay. It's also possible that T star could be T. What if starring does nothing? What if T star is T? And there's a word for that. So this is a definition. Given T, linear operator on an inner product space V, we say T is self-adjoint. Self-adjoint if T star is simply T, if it equals its own adjoint. And I don't know why the emphasis in the pronunciation of this word is different, because we don't say self-adjoint, we say self-adjoint. But the map itself isn't called the adjoint, it's called the adjoint. Anyway, that's what self-adjoint means. And if you want to see it more in terms of the inner product, it just means this. That is TV with W comes out the same as V with TW, because T is T star. So that's for all V and W in the space. So sometimes T star turns out to be T. These self-adjoint operators come with all sorts of additional structure that will allow us to study them much more definitively than some arbitrary operator on an inner product space. And the last order of business today is to make a little observation along those lines. Theorem. If T, a linear operator on an inner product space V, is self-adjoint, then all eigenvalues of T are real. So self-adjoint operators are nice in that their eigenvalues are all real. So whatever eigenvalues there are, they have to be real numbers. And the proof is really straightforward. Okay, so let's suppose we have an eigenvalue. Suppose lambda is an eigenvalue with eigenvector V. All right, we're trying to argue that lambda has to be a real number. Okay, well, check this out. On the one hand, if you do TV inner product V, well, V was an eigenvector that went with lambda, so that's really lambda V V, and that's really lambda magnitude V squared. On the other hand, since T is self-adjoint, TV inner product V is the same as inner product V TV, because T is T star. And again, V is an eigenvector that goes with lambda. So this is V inner product lambda V. Now that lambda can be pulled out in front, but it comes out as a lambda bar because we have, what, conjugate homogeneity in the second slot. Anyway, that pops out as a lambda bar in front of everything, and you're left with norm V squared. So look at that long string of inequalities there. Thus, lambda must equal lambda bar. In other words, that scalar lambda is a real number, because if it weren't, that wouldn't be true. That is, lambda is real. So you got a classic fundamental linear algebra fact that anyone who has taken 406 just stores away for use forevermore. And that is, if you have a self-adjoint operator, its eigenvalues are real. Okay, so we're going to start exploring self-adjoint operators, and we're going to try to classify them. We're going to see, all right, what are the operators that are self-adjoint? What are they really, and what can we say about them? Read continued in 7A. Come to class with questions, and we'll start getting some problems to work on this Friday. All right, see you next time. Bye.